Okay, so a few.
Are we recording now? All right,
Right.
so everything now is on the record?
And streaming.
Oh, yeah, and streaming. So the internet is watching.
Oh, streaming. I thought you said screaming. I'm like, yeah, screaming is getting recorded too. I'm trying to do that.
Old Shmoocon, I'd ask if you're going to throw this, don't throw it in a room where they have wonderful devices that might disintegrate if you hit them too hard. So feel free to toss that at a different speaker or use the virtual Shmoocon technology. Hopefully slightly less docile than earlier reversions of it. Shmoo mouse pad for somebody back there. All right. So again, some additional t-shirts from some of our sponsors. This one is Security University again. So, Sinestro is the arch villain of what DC comic superhero? Whoever that was. Here, pass this shirt on the way back. Shmoocon registration desk.
Cool, thank you. I thought you were... So today we're going to talk about chiromancy. Shave first. Thank you. Yes, shave first. Chiropractors, however, they speak to my back and great things happen. It's a good thing. So today we're here to talk about sub-gigahertz radio. What's a gigahertz? Anybody who doesn't know, please leave. If you've been to a talk of mine before, you know that I like to walk around. Today I will not be walking around, I will be limping around. Because I visited my good friend Cutaway and decided it was a good idea to kick a cement wall barefoot. Yes, I know.
He was frolicking through the beach. He was frolicking through the waves with his wife.
In January, the water is perfect. So today we're going to talk about one of my favorite topics. Well, first of all, what is this little sub-gigahertz thing that we're talking about? Why do we want to be there? And then I will release a tool by the end of the weekend to help you get that much closer to tickling these things that are wireless. If you're a ham operator that's created 6 dozen radios and this is kind of boring to you, I hope there will be a lot of humor and enjoyment anyway. So intro to sub-gigahertz. So an international commission put together a plan for using wireless spectrum. Wireless spectrum being something that we can't hear and we send electricity through the air, right? In so doing, they created what's called the ISM band, the Industrial, Scientific, and Medical bands of spectrum. So you probably have used some, like, I don't know, 2.4 gigahertz, 5.8 gigahertz if you've got one of the newer phones. Your cell phone lives in this range. The 3 that we're going to focus on are 315, 433, and 915 because they're all below the gigahertz line. There are the 2.4 and the 5.8, and there are others as well that are less common. There's another Shmoocon chip that plays in these other areas, and I'm thinking that we may take this tool and port it there. Makes have a lot of fun. Maybe give Travis something else to hack. So what is sub-gigahertz? What plays there? Well, sexy girls wearing insulin pumps, that's one of my favorites. But your cell phones, so cordless phones, I found a lot of cordless phones hit 900 megahertz. I like that because it doesn't cause my Wi-Fi any problems. Car remotes, 315 megahertz typically, sometimes 433. You've got the TI Chronos watch. I love the Chronos watch. Why? Have I done anything with it? Absolutely not. But it comes with this free dongle that I've been using to do this whole deal. So $50 is not exactly free, but I get the watch, or I get the dongle for free, and I chose to do it the other way. I am me. Anybody heard of that?
Yes.
Woo! Yes, thank you for the gentlemen who have Travis and Mike Osman for writing some of the code that I've used and loved the most. Power meters. Power meters live typically in the 900 megahertz range, sometimes 2.4, and there are a couple of vendors, I think at least one vendor that's doing licensed spectrum that they want to pay for. So much more, including your own custom stuff. How do we play with it? When I got into hacking certain embedded systems, one of the big problems was, how do we talk to these things that use proprietary communication on an ISM band that, at the time, I was relatively new to doing radio. So the big ramp-up speed for security researchers, I was a software guy, obviously, it was too steep of an incline to get up to speed in a time that was at all feasible for companies to pay their people free, if they're not getting paid for this, or to charge a customer. So I've spent considerable time, and a lot of it actually paid for by a power utility who has been very, very good to me, to ramp up to speed and to come up with a tool set that is what we're talking about today. It's called, of course, RFCAT. Why? Because RFCAT is your friend. So there are currently 3 types of devices that this toolkit supports. We've got the IME dongle, or I'm sorry, the IME. I'm working on getting the IME dongle into it. There's called DONS dongles, otherwise known as the Shmoocon 1111 EMK. I say this because I've been focusing so much on the Kronos dongle, and Cutaway shows up with one of these things. I'm like, what's that? There are some catches. Sure, a radio will get you into the spectrum, but to talk to a given device, you have to know how it's configured on a file layer. So your baud rate, how are packets pieced together, what's the sync word, what's the frequency, is it frequency hopping? If it's frequency hopping, you've got to figure out how to sync up with and keep up with the FHSS. One of the other catches is Bluetooth plays in this range, and I'm sorry, that's a PHY that my hardware doesn't support. It's called direct sequence spread spectrum. The stuff that I'm focused on is more generic frequency hopping spread spectrum. The difference is FHSS systems do a couple bytes before hopping. DSS systems actually break in the middle of bytes. They just send a couple bits and then they hop to the next channel. The code is not there at the moment, but you will be able to find it during the weekend. rfcat.googlecode.com has the latest checkout.
Is that lack of support a architectural gap, or you just haven't gotten to it yet?
For Bluetooth?
For DSS versus...
It's actually a hardware limitation.
Repeat the question?
Thank you, Nicholas fucking Farr. The question was, is it a limitation of the hardware or just the fact that we haven't gotten there yet to support Bluetooth using the dongle? And the truth is, Bluetooth, in order to achieve the DSSS that it does, has a special hardware so that it can switch channels fast, a lot faster than the hardware that we've got. So why do I care? You're here. You're sitting there going, yay, yawn. Why do I care? Why should I be here? Well, because I believe that there's an inner geek inside of all of us that just loves RF, first of all. Secondly, your security research may lead you down a path where you need to create something that doesn't exist. Or you get into a position that maybe it does exist, but you want to know more. Maybe there's a network adapter that you can purchase, but it hides all the details of actually how to subvert the system. And your own organization, if you're not a security researcher all full-time, but your organization uses Telzon gear for plant automation and management, or some of the other 900 megahertz systems out there. Sorry, I didn't mean to get a plug to a vendor like that. you may want to do research and see just exactly what is going over the air unencrypted. I know telnet sessions have been long running over 900 megahertz unencrypted. A little bit of intro to the chip that I've selected for the tool set. The Shmoocon 1111 radio uses the Shmoocon 1101 core, which is a radio. It has a microcontroller that comes alongside of it, similar to the Shmoocon 1110, which is in the IME. The difference is the Shmoocon 1111 also adds a USB controller. And that became very important because while doing work in the power systems, we wanted to create a dongle that we could, basically a network adapter that we could just plug in and go ahead and attack stuff. So it's based, it has a, we're going to talk a little bit about the microcontroller, a little bit about the radio state engine and how much pain that it caused me, and how to configure your radio. We will touch briefly on USB, and we really won't get past timers and DMA except to say that you configure them using registers in the microcontroller. The Shmoocon 1111 microcontroller is a modified 8051 core. Raise your hand if you know what an 8051 core is. Some of you? Okay. 8051 is probably the most widely used microcontroller core available. You probably haven't run into it directly. You've probably just simply used microcontrollers that took the 8051 core specs, because they're widely available, and wrapped it into their own thing. That's what Shmoocon did. The 8051 core has some very interesting limitations, like 256 bytes of RAM. Who would ever need more than that? Special registers that allow you to configure the chip, and various memory spaces. 8051 core is actually typically seen in Harvard architectures where you separate code and data. In the Shmoocon case, they just said, okay, screw all that, we're going to throw it all into one address space, and we'll just call this address space X data. And guess what that means? That means that Travis, a year ago, was able to take his good FET, tap it onto an IME, shove code into RAM, and execute it. It also means when we do exploitation, we can do the same. The Shmoocon 1111 itself has 4K of RAM. This is a limitation, but if you're careful with your RAM usage, you can do good stuff. One of the cool things about having a microcontroller with a radio core, USB controller all wrapped into one is that the designers made this 8051 core have access to special registers to directly access the radio. So in other circumstances, you have a microcontroller, you have a radio, and you have a SPI bus between them that you're bit bagging the whole time. By wrapping it all into one, you simply write your code to access registers, and it's just like accessing memory. Right, again, there we go. Shmoocon 1111 state engine. So we know how to write code, right? We probably have written some Windows code, correct? Hands? Windows, Linux, both. Wrap it all into one. Awesome. Very cool. I saw how many where my hands went up when I said Linux code. So microcontroller code is a lot like writing all those code, the code for a modern OS like Windows or Linux, except that you manage the entire thing from start to finish. So you typically in Windows or Linux have a protected memory space where you have your own little process and it talks to an operating system and all this stuff. No, not quite so much. You control the entire hardware. You start with your main function. And when main is done, well, the hardware decides what to do, whether to restart or just hang. So we understand how to program. The thing that we have to now think about is the fact that you have a program that has state. You have interrupts that trigger, and you have to manage the state of your program and of your microcontroller such that you don't have race conditions and all this stuff. And your code can run really, really well. But if you don't understand that the radio has its own state engine and its own timing stuff, you will be screwed and not be able to write code for the radio. I know this because I spent the first 3 months of playing getting hung up on the fact that I have to tell the radio what to do, and then, oh, my code has to sit and wait until it's ready. I also have to know something that I'll get into in a few minutes. When I reconfigure my radio, I need to tell it to go into the idle state. Then reconfigure, and then shove it into RX or TX. You can't just leave it in RX and reconfigure it. Sorry, that was like 2-3 years ago. I'm not that stupid anymore. Configuring the radio is as easy as poking or peeking at registers, or basically accessing numbers in your program. Numbers in memory, 1 byte numbers in memory, that's how you think about it. So you've got things like modem control. You've got 5 registers that control modem control, and each of those 5 registers has various bits designed to control various aspects of the radio. But, nice talk. So you'll see, if you read my code, you'll see a lot of anding and oring of bits to manipulate these registers so that I don't clobber other configuration. Packet control, you've got 2 registers. You've got a few for frequency synchronization. Frequency synthesizing. And a few others to decide how the radio works. Who here realized that a digital radio has a modem? Some of you? I found that eye-opening when I first saw it. It's like, this kind of makes sense, since radio is kind of analog and transmitting digital data. Turns out, having your modem set up correctly is very important. A couple other things, you can set your frequency, your base frequency with a freq 2, freq 1, freq 0. Your radio state engine decides what happens when I'm done receiving in the state engine. So does it go back to idle, or does it go to TX, or does it just stay in RX? Very important stuff to keep track of. You can control your channel with the channer register. I don't know, I just think that they like saying channer. So what kind of channel are you on these days? They also represent, they introduce an optional address register. So it's the next byte after your sync word. But I tend not to use it because the stuff that I'm doing is proprietary and it's made for using with a lot more than just 256 things. So typically the proprietary stuff that I'm using, they design their own address mechanism. They don't use the chips. And then there's automatic gain control, AGC. This is the stuff that allows your incoming messages to be amplified before you start sampling them. If you are not a radio engineer, we learned this the hard way, didn't we, Cutaway? If you're not a radio engineer and know better than the people who wrote SmartRF Studio, start with SmartRF Studio.
Start with SmartRF Studio.
What do we start with?
SmartRF Studio. Let's chant it. All right. Yeah, we must have hacked for hours on something, and then SmartRF Studio pops up in somebody's VM, and they're like, "Oh shit, it works now."
You need, hang on, you need to specify that. We hacked on it for hours, and then we talked to Travis again. He said, "Listen to what I've said the first time. Start with SmartRF."
Yes, thank you for that.
Read the comment.
Thank you. Travis is really brilliant. That's not what he says. Do what he says, and don't say, "Yeah, donut." Yeah, got that. SmartRF Studio allows you to select your frequency, your baud rate, and basically give you like known good settings for whatever speed, typical speeds that you'll be wanting to play with. So they will give you all the registers needed to set up your radio to talk at that baud rate on that channel with that type of communication. A couple notes that you can take with you, I hope. Data rate, bandwidth, intermediate frequency, and frequency division or deviation, they depend on each other. You modify one, And you may have to modify a couple others in this group in order to get the best performance. This is one of the things Smart RF Studio does for you. If you want to learn about that and you're not an RF engineer by nature, or even if you are, go to Smart RF Studio and do some differential comparisons. I think you'll take away a lot. Put the radio in idle state before configuring it. Also, put the radio in RF idle state before configuring it. And one last time. Yeah, you get the point. Lots of pain. You control the radio by sending it strobes. So it's kind of like this little connection between your microcontroller and the radio state engine. You just kind of say, I'd really like you to go to this now. And then, wait for it to get there, you're accessing a register called mark state. Mark state is basically the radio state. So there is a setting in there, or a state in there settling. So dude, I got what you said, I'm still working on it. And then when it gets to the state you want, then you can move on. USB is a massive world of its own. I would love to get into it here, but as I said, it's already way too many slides. But here's a slide for you. You can download it later. A little bit about how our code provides USB access. How you can modify it to turn your RF dongle into a keyboard, or a mouse, or some other hacky thingy. And USB for developers. So we're trying to hack radio. What kinds of things do we want to know? So we basically need to reverse engineer or obtain information about our target system. What kinds of things are important? Frequency, first of all, or frequencies if it's a hopping system. Modulation, is it an FSK? Is it an MSK? OOC or others? We want to decide, I meant to take that out of the slide. We want to decide upon an intermediate frequency. This isn't really so much what they're using, it's more about what your Shmoocon dongle, your Shmoocon chip is capable of handling. You want to determine the baud rate. You can get close in baud rate and you'll start seeing strange bit oddities. You want to identify channel width. So for hopping systems especially, channel width can be like 200 kilohertz wide or 250 kilohertz wide. And the channel width will determine where your next channel is. So as you're hopping, this will be very important. I have one right now that has a channel width wider than what the radio will do, and I'm actually having to multiply the channel by 2 so that I can use this dongle and still play in the same space. Bandwidth filter. So as we are focusing the radio signals, as we're focusing the radio signals into a range that we can actually turn on an ADC, a sensor, basically like a sound card, plug in a radio into your sound card. Sound card can't handle really high frequencies, but if you channel the higher level RF down into a lower frequency range, basically your sound card can be doing radio. In fact, that's the basis of the software radio logic, the new radio, and other SDRs, software-defined radios. We want to understand what sync words are there. How do we know when a packet begins, is what sync words tell us. We want to know if it's variable length or fixed length packets. Are they using CRC? Are they using data length? We'll talk about that in a minute. Are they using some sort of encoding? So frequencies, if you're looking to attack a certain type of thing, sometimes there's a range just that most things that do that awesomeness live in. For example, a lot of car fobs live in the 315 megahertz range. There is a special designation for medical devices to live between 402 and 406 megahertz. That doesn't mean that they're all there. 868 is really common in Europe. 915 is really common here. 2.4, 5.8, they're everywhere. A little bit about modulations. We have basically modulations, forgive me, this is very basic, but modulations is how we take a carrier wave in base of time. This is a frequency wave. How do we modify frequency wave to stick data into it? How do we deviate it from its standard sinus wave to stick data into it and then pull it off again. So we've got frequency shift keying. This is like FM for digital feed, folks. Frequency shift keying, seen in the top, we slow down the frequency or we speed it up, given whether we want a 0 or 1 or other data involved. As opposed to amplitude shift keying, or ook. Who here can tell me what ook means?
On-off keying.
On-off keying. Do you think that may be related to amplitude shift keying? Yeah. Well, because your amplitude is 0 or it's 1, right? Kind of. So this is AM for digital. We couldn't keep the old names because you'd probably be brought back to that drive-in theater with a really nasty sound because you're using AM to listen to the movie. Who here's been to a drive-in theater? Yes, thank you. Glad I'm bringing out some of the old folk. This chip also provides support for minimum shift keying, which is a type of FSK. It's a special type of quadrature phase shift keying. And it is used for things like GSM. So, gee, I think that might be an interesting thing to use the dongle for. You can't hardly see it, but the frequency is actually shifting in the bottom picture here. I think that's why it's called minimum shift keying. Intermediate frequency. So I had a very interesting run-in with IF and the concepts of IF right now. And intermediate frequency is, I'm going to make this backwards anyway. The intermediate frequency is used with a local oscillator and the radio frequency. What's that? What's that? Yes, thank you. The term is heterodyne. You probably have a super heterodyne radio in your car, right? The idea is you take a high range RF signal, like 108 megahertz, and you heterodyne it into a intermediate frequency using a local oscillator. This is not making sense to some of you. Bear with me, I'll make it make sense. The local oscillator, or the intermediate frequency, then can be amplified. It can be treble, bass added, all that stuff. And it's really easy to have components in your radio that don't have to move all around. They just focus on that one intermediate frequency. The heterodyning makes it so that the 108 megahertz transfers down into the same intermediate frequency as 88.7. That's why you don't see any real significant differences for your radio channels. Same thing. How do they work? You typically have a local oscillator that is at a certain frequency. Okay? So let's just say 400 megahertz local oscillator. You then have your radio frequency range, let's say 915 megahertz. Your intermediate frequency comes from the combining of these two. Actually, let me go the other direction. Please forgive me. So let's say you have a radio operating at 400 megahertz. You've got a local oscillator operating at 1.3 gigahertz. Add them together and subtract one from the other, and you get sidebands around the upper frequency, the upper oscillator. So if you do, let's see, 1.3 gigahertz minus 400 megahertz, what's that give you? 900 megahertz, right? Do my math now, right? Okay. I've actually seen a radio setup doing that very thing. They have a 400 megahertz radio, a 1.3 gigahertz local oscillator, and they're targeting the 902 range. So what do they do with that other side? Because it's the intermediate, another frequency up on the other end of 1.3 is going to be transmitting or receiving as well. Well, they filter that out so that it can be ignored. The idea of determining an intermediate frequency with a Shmoocon 1111 radio is what the ADC is capable of handling with the least amount of noise. This is something that I recommend highly that you trust SmartRF Studio. It is dependent on the baud rate, because your baud rate is going to determine how clean the signal has to be, how much bandwidth is used. So your baud rate, much like the modems of old, in fact I intended to have a picture of an old modem there. The frequency of bits. So you send ones and zeros down the line, and you expect that the other side understands the same, that they're listening in the same speed rate, right? Well, if we get it wrong, that can be interesting too. In fact, if you are three times as fast, or three times as slow, you can start to see ones and zero bits printing out basically garbage, but a lot of the same garbage that you would see if you were on the right speed. In embedded stuff, I'm seeing a lot of 2400 baud, a lot of 19.2, 9600, 38.4, and 250 kilobaud. Channel width is the idea of breaking your channels up into a specific spacing. For example, your 802.11 stuff has a very wide channel width, whereas Zigbee in 802.15.4 uses the same spectrum range, but they have very tiny channels so that they can live in the same spectrum as Wi-Fi without clobbering each other. Your bandwidth filter allows you to determine, or allows you to ignore a lot of signal that isn't important so that your ADC is not dealing with way too much noise. So we have RF floating through the air all the time. EMI, electromagnetic interference, is causing all sorts of radio to happen all the time. So your radio is being bombarded by bits. In order to determine that we are actually talking to another radio at the same baud rate, we have what's called a preamble. That is a 1010101 pattern over a certain amount of time. At the end of a preamble, we'll often see what's called a sync word. This means 2 or 3 bytes that are specific and known to each party on this network. That when the radio decoder sees this sync word, it says, okay, we're ready for a packet now. As soon as that sync word's done, the packet begins. This is how we make sense out of chaos. If you are interested in seeing what kinds of things are working in a spectrum or on a channel, setting no sync word or setting the sync word to hex AAAA can provide, oh wait, hex AAAA, that looks a lot like the preamble, right? So that allows us to trick the radio to just sending us whatever bits show up as long as we see the preamble. So the sync word should end up being one of bit shifted around in the data that we receive, and we can make sense out of it later. The Shmoocon 1111 has 4 basic ways to look at how to do preamble and sync word. First of all, none. They just kind of send data at you. I love this. This is a great way to tell that my radio is actually still working. Carrier detect. So if the RSSI, the signal to noise ratio gets high enough, then we figure, oh, something's on this channel. And it'll start sending data, even though it's not identified that there's a preamble, so we don't know if it's talking to us on the same baud rate. But we know something's there. That's important. We also have sync word matching, where we match 15 out of 16 or all 16 out of 16 bits of the sync word. That is another mechanism, that's another state that allows the radio to continue. If we set that we only want packets where that matches 15 or 16 out of 16 bits, we clean up what kind of noisy packets we're getting, but we don't need to see all the other interesting noise that tells us about what's going on in the spectrum. There's also the option to double the sync word. I hate that it's called 30 out of 32 bits, because in reality it's just 16 bits duplicated. But it's a configuration setting that the radio supports, and it is actually the default for many video radios. Variable versus fixed packet length. Variable packets, the only thing you need to know here is that variable length packets put the size in the first byte. If you don't want to be dependent upon that first byte being anything in particular, we set it to fixed length, and we tell the radio that when you time out, then just send me the packet, and we'll deal with it that way. The radio does support CRC. Here is the radio packet as it gets sent out over the wire with data whitening, forward error correction, and CRC optionally enabled here. It shows the, Kevin, I don't agree with you. I don't agree with you. The laser is a very helpful tool. Is that? When it works, yes, thank you. So we see here the preamble bits, the sync word, the length field, that's if it's variable length, an address field, again, optional. Our data, and then a CRC16, 2 bytes are tacked on at the end when CRC is enabled. So as you can see, the packet that as the packet demodulator sees it can look very different based on how we configure the radio. This is very important for setting up our packet handler to understand what we want. So oftentimes when I'm searching for stuff, I'll turn off the length field by setting the fixed length. Turn off the address field, and I'll turn off CRC. So that, hey, if they send me CRC, I just kind of get it, and it's okay. I just want to know that the data is there. Data whitening and the pain that it brings. RF data really wants to be random bits. It just makes sense to have not long sequences of zeros or long sequences of ones because there's not enough entropy for the radio to stay on course and understand long sequences of zeros. So one of the things that the radios have added to take normal traffic with lots of zeros back to back and whiten it a little bit. So they'll take a 9-bit sequence and they will simply XOR every bit with this 9-bit sequence. And when you run out of that 9-bit sequence, it continues at the beginning and it just rolls over the data, basically allowing you to have a lot less of the same bit back to back, or at least hopefully. We have also Manchester encoding, which also tries to solve this problem as well. Manchester encoding ensures that in every bit there is at least one transition from 0 to 1, 1 to 0. This allows for never having all 32 zeros back to back, at least over the air, because the Manchester encoding makes sure of it. We also have something called forward error correction. There are several different models. The type that the radio supports in it is called convolutional. The radio I'm trying to type right now is using, it's probably, no, Reed Solomon. Reed Solomon is just another way of adding more bits to a pattern with error correction built in so that if a few bits get messed up, and trust me, RF bits get messed up, we can still figure out what the packet was intended to be without having to retransmit. So I've been doing a lot of MAC layer stuff. Remember MAC layer stuff? There's no TCP at the MAC layer, right? So if it gets messed up, we've got to figure that out and send it again. So the forward error correction allows us not to resend so many things, which speeds up data a lot. The chip also supports AES. And I love the AES crib sheet, so I just threw it in there. Give you a little example of how the registers are broken down. If you look at the TI documentation, which I hope that you will if you write new program stuff for the tool or modify the radio at all, you'll see bit 7 here is a DC filter off. Your modulation format is set in bits 4 through 6. And then you can do list, 2FSK, GFSK, the Gaussian FSK. or whatever. Your Manchester encoding can be enabled in the same register, and then your sync mode is configured in the same register. So lots of data packed into one 8-byte or 8-bit register. And while doing research and